Hello, it's Keith here, and this is lesson 36 of the simple series of my Z80 assembly programming tutorials, and we're looking at the Game Boy today, and we're looking at a simple sprite clipping tutorial. Well, I say sprite clipping, it's actually using the Tilemap. We've got our Chibiko mascot on the screen here, that's the character here, and we can move it around the screen, but it can now go partially or even entirely off the screen. Now, the graphic we're drawing today is being drawn with the Tilemap, so it's not technically a sprite, but we will extend this next time and we will use Hardware Sprites. The reason I do this first with the Tilemap is I think it's a lot easier to get simple graphics onto the screen just using the Tilemap, because you don't have to worry about hardware sprite counts or how many sprites are on a line and things like that. But obviously we do have limitations by doing this. We're moving in 8x8 chunks, but it's simple enough to get started, and so we will look at this today. Now, before we go into the full example, first we need to discuss the concept of logical units. So let's go over to the projection screen and let's have a look at my diagram here. So this tutorial I've ported to all kinds of different systems, and it poses a problem. These are 8-bit systems, so I want my X and Y coordinates to be 8 bits, but a lot of these systems use a 256 by 192 screen, or even more sometimes. And so to have a sprite partially off the screen, we need to have a coordinate system that allows for that kind of size screen, but allows for the object to be partially or even entirely off the screen. So what I've done is I tend to work in a logical unit system where one logical unit is 2 physical pixels. Now on the Game Boy, of course, this isn't actually so much of a problem because the screen's tiny anyway, but as I say, working in a common way on all systems makes porting games a lot easier and allows me to keep at least part of my sanity when I'm working on so many systems. So that's what we're doing. So our tiles with their patterns that are 8x8 pixels wide are now 4x4 logical units, and you will see that in various parts of the code. So that's what we're doing. And in the example here, you can see we've got this little picture here. Well, in this case here, the visible part of the Chibiko graphic would be this top corner here, and the rest would be outside of the visible screen. Okay, so that's logical units. Let's now discuss the concept of the cropping algorithm that I'm using today. If I go over to the Blackboard screen, and I apologize if you've seen this before, I have to do it many times and I'm quite sick of doing it, but a lot of people won't be watching all the tutorials, so off we go. Okay, so we've got our screen here, this is our screen, and we've got our sprite here, this is our sprite, so there we go. And our sprite moves around the screen, which is what you'd expect a sprite to do. And the problem's only going to come when our sprite goes partially off the screen, and we're going to need to do something about it. Now, of course, the sprite in question today is actually a graphic made up of a sequence of tiles. So we're going to need to start removing those tiles and drawing a few of them on the screen. Of course, these will be in 8x8 pixel blocks because that is the pattern size on this system. Now, if our object goes off the top of the screen, we will need to remove the tiles in this part here. It's a shame this screen isn't more square. I should have drawn it a bit better. Anyway, we would remove this part and we would only change the height to this part. So we need to skip these tiles here. That's if it goes off the top of the screen. But what about if it goes off the bottom of the screen? Well, in that case, well, we don't need to skip anything, but we would just need to change the height of the object to that. Very easy. Now, if it goes over the left-hand side of the screen, it gets a little bit more interesting. We would change the width, of course, and then we would skip this first set of tiles here before we start drawing the line. Now, we're drawing our graphic in a zigzag format like this, and so that means that we would skip the first part, and then we would also skip a part after each following line. So we would then skip this part here. So that's what we'd have to do on the left-hand side of the screen. On the right-hand side, though, slightly different. We wouldn't need to skip anything before the first line, but after each line, we would need to skip this part here. And of course, we need to change the width as well. The tricky thing is, of course, well, we might need to do multiple things at once because we might be at a corner and we'd need to change various things. And as I say, the Chibi game couldn't do it correctly because my code was horrendous and very buggy. It's less horrendous and less very buggy today. It's possibly vaguely tolerable and only slightly buggy. Anyway, it's what we've got, so let's go over and take a look at it. Okay, we've seen you already, go away. So this is the code that makes up today's example, and so we'll be looking over this today. Now, what I'm not going to do is I'm not going to cover the loading of tile pattern data, the drawing of the very basic tiles onto the screen, or the joystick reading. This has all been covered in the Simple series before, so please take a look at the other Simple series episodes if you need to know how to do that. Now, we are using some virtual IX and IY registers here. Now, the Z80 has IX and IY registers. The GBZ80 does not, so I'm using some entries within the memory, and I'm simulating those functional values as a 16-bit pair here on this system. We also have a visible screen bank because we're actually using a double buffer today. So we are drawing the Tilemap in one buffer and then we're swapping the visible buffer over to reduce flickering, and we have this sprite h clip value, which is a word value that is a number of bytes to skip after each sprite, because as I say, if I get my sprite stick here, when our sprite goes off the left or off the right, well, we're going to need to skip some tiles before the next line. So that's what we're going to do there. Now we're defining the visible screen as 128 by 96, and you might think, well, why are we defining it as that? Because the screen on the Game Boy isn't that big. It's only 20 tiles by 18, I think it is. Well, the actual tile map is bigger than the visible screen, so if we wanted to scroll the tile map, so we're working on the actual tile map itself, which is 32 tiles wide. So that's why we're using that larger area. And as I say, this is the sort of standard area for all of my other systems. So that's what we're doing. Now we've got various code here. First of all, let's have a look at the page flipping routine. We'll just quickly cover that. So basically on the Game Boy, we have two memory addresses that can be used for the tile map. Basically the tile map can be either at memory address 9800 or 9C00. And so these are the two possible tile maps, and these are defined by one of the bits at port FF40. And the bit in question is bit 3, and this is the B bit, the lowercase b in this byte here. And the B bit will select the tile map address, with the 0 being at 9800 and a 1 being at 9C00. Now our visible screen bank byte here is actually going to contain the top byte of this 16-bit address, so a 98 or a 9C. And so we're masking out one of the bits and we're shifting it to get it into the correct position here. And then we're XORing it for the next iteration. So running this page flip routine will flip the visible bank, and it will also change the byte in the visible screen bank value that we're using to calculate our VRAM destinations. And if you look at the get VDP screen pos function, which will calculate a VRAM destination from an X and Y address, the X and Y address being in BC in tiles, well, this is loading in the visible screen bank byte and adding that as the base for the tile map that we're drawing to. And as I say, it will be a 98 or a 9C. You can see at the start of the code, we're initializing it to 98 here. And so that's how we are doing our buffer and our flipping. Now, what about the drawing routine? Well, all of our coordinates now are in logical units. So our graphic is 6 by 6 tiles, but it's 48 by 48 pixels. Now we're working in logical units, and 2 pixels is 1 logical unit, so it's 24 by 24 logical units. Now the IY pair is going to be the first tile number that makes up our sprite. Now our graphic has been loaded into the patterns 128 and onwards, and so we're loading 128 into the IY pair here. Now we're going to run this do crop routine, and this do crop routine might need to skip parts of our graphic turnaround if our sprite is off the top or the left hand side of the screen, and so it will alter that IY pair as required. The other thing the do crop will do, as well as changing the XY position, width and height and the first tile number, is it will set the carry if the sprite is entirely off the screen, telling us to give up and don't do anything. So let's take a look at that do crop routine right now. Okay, so here it is. Here's the do crop routine, and first we're clearing the sprite h clip to 0. Now the sprite h clip is the tiles to skip after each line, so we're going to assume nothing to be clipped. Maybe we were right, maybe we were wrong. DE is going to be used as a pair of temporary variables, so that's what we're going to use that for. Now when this routine runs, the BC pair are the X and Y position in logical units, H and L are the width and height in logical units, and as I say, IY is the first tile number. So we're going to do that. Now we're going to first consider the top of the object of the sprite, as I will call it. As I say, it's technically a tile map graphic, but I'm calling it a sprite for today's purposes. So we're loading in the Y position here, and then we're subtracting the minimum Y position of the screen. So this is effectively, if our Y position in logical units is negative, this is going to push the accumulator into a negative value here. Now if it's not gone negative, then basically we must be somewhere entirely below the minimum Y position, so somewhere physically on the screen, or maybe off the bottom, but definitely not off the top. If we are off the top though, we've now got a negative value and we need to convert it to a positive, but the GBZ80 processor doesn't have a neg command, so we're simulating one with a complement, flipping the bits, inking A, adding 1, and that will convert a negative to a positive. What we're now doing, we are partially off the top of the screen somewhere, and so what we're now doing is we're effectively rounding up the number of tiles to remove. So we're adding 3, and then we are removing the bottom 2 bits because, as I say, there's 4 logical units to 1 tile pattern, so we're rounding up to a number of tiles here basically. Okay, what we're then doing is we're comparing to the height of the sprite in logical units, and this is basically to check if our sprite is entirely off the screen, because if we're somewhere way up over here, then, well, this will be very negative and the value at this point will be greater than the height of the sprite. So in that case, we're jumping to all off screen. All off screen, well, you saw before, if the carry was set, we were returning, and all off screen does is sets the carry and returns, telling the calling routine, give up, there's nothing to do. Okay. Well, if that's not the case, then we're updating C, our Y draw position. We've now subtracted the minimum logical unit, and so we're one step closer to a value that we can actually use to draw data to the screen. We're still in logical units, but we've now subtracted the minimum Y, so our Y position will now be 0 based rather than based on the centralized logical screen. So we'll need that later. We're then adding the height of the sprite, and we're subtracting the height of the screen in logical units. And if this has caused a carry, then our sprite is clearly within the logical screen. Otherwise, it must be partially off the bottom or entirely off the bottom. And in that case, well, again, we're rounding to a number of tiles, comparing to the height of the sprite, and if it's the entire height of the sprite or more, again, we're entirely off the screen. And so in that case, we don't want to do anything. Now, in both these cases, we've stored the amount to remove from the top in E and the amount to remove from the bottom in D. And so we now have these two values, and we can now update our sprite as required. So we're going to combine these two together, and if there's something to be removed, we're converting it to a negative value, and we're effectively subtracting that from the height of the sprite, because whether it's off the top or the bottom, the height needs to be changed. What we're then going to do is we're going to take the amount to remove from the top, and we're going to convert it to a number of tiles. We're then going to take the width of the sprite, of the object, and convert it to a number of tiles. And what we're going to do here is we're going to remove all of the tiles from the starting position for when we've cropped part of the top of the sprite. We need to skip some of the tile patterns in that IY pair. And so what we've got here basically is adding the E part to the IY pair D times, and this is using the values that we've calculated here based on the amount removed from the top and the width of the sprite here in tiles. So that's what we've done there, and that's removed any part for the top of the sprite. Now what we're going to do next is basically the exact same thing for the X position, because we need to now consider whether our sprite's off the left or off the right. So that's what we're going to do. So we're resetting the DE pair. We're going to set them again in a moment. We're loading the X position, subtracting the minimum X, and again, if this has gone negative, then our sprite must be somewhere off the left-hand side like this, and so we're going to deal with that. So we're converting that back to a positive, we're rounding up to a number of tiles again, and we're comparing to the width of the sprite, and if it's the entire width of the sprite, well, we're entirely off the screen, so we're going to jump to all off screen. We're then storing the amount to remove from the left, we're setting the X position to 0, and we're updating the X position here, and then we're doing the same for the width here. So we're adding the width, we're seeing if this is partially off or entirely off the right hand side of the screen by subtracting the width of the screen, and again, if this has not caused a carry, then we must be somewhere like this, and we need to again do our cropping. So we're comparing to the width of the sprite, and if it's not the entire sprite, we're storing the amount to remove from the right in D. Okay. So what we're doing now is we are taking D and E, adding them together and converting this to a number of tiles, and we're storing this in sprite hclip, because either side we need to skip some tiles after each line of our draw, because as I say, we're going to draw our Chibiko bitmap. It's 6 by 6 tiles, so we go across and then down, but if it's partially off the left or the right, we need to skip some of those tiles each time, so we're storing that in sprite hclip. We are then converting this back to a number of logical units. For now, we're still working in logical units and storing that in D. We're then calculating the new width in logical units, and we're then going to update the IY pair for the start bytes based on the amount removed from the left. If we're on the right, we don't need to remove anything from the first part of this image, but if we're off the left, well, that fireball needs to go, so we would need to remove that. And that's what we're doing here. We're basically taking the amount to remove from the left, converting it to a number of tiles, and we are then adding that to the IY pair here. A little bit crude here, but as I say, we don't have the IY registers themselves. The final thing we're doing here is we're converting all our logical units into physical tile counts. We're just shifting, basically dividing by 4 in all cases here. We're then clearing the carry and returning. So that's telling our calling routine the actual position and the actual width and height in tiles to draw to. And that's what we will do, because once we get to this point, the fill area of tiles, this has now got physical dimensions of our object to draw to the screen. So we're calculating, this is basically the same as the original version, we're calculating the end position of the drawing here. We're using getVDP screen pos to calculate the VRAM destination within our tilemap, and we're then basically loading in the tile number we want to write, waiting for the video hardware to be ready. We have to wait for H blank or V blank, and we're then storing the tile numbers to VRAM here, and we're just going to do that repeatedly. Now, after each tile's been drawn, we're incrementing the tile number for next time, and then we're repeating until we've done an entire line. Now, once we've done an entire line, we're updating our IY pair to skip any tiles that might need to be removed. Now, maybe there's none, maybe that's 0, but it's quick enough to just do that after each line, so we're just doing that whether it's 0 or not. And then we're just repeating until we've done our entire graphic. And I say nothing too complex here. It's pretty straightforward. And I say mostly it's the same as before. So there we go. Now, as I always say, you can go to my website and you can download the example code for today. And if by some miracle it's useful to you in some amazing program you're working on, go ahead and use it. You don't need to give me credit. Best of luck to you. We will be looking at this again. Next time we'll be using Hardware Sprites though, so we'll be getting a little bit more adventurous and doing some nice smooth movements. So if you've liked what you've seen, please like and subscribe so you see that. Anyway, I hope you've enjoyed this today. Thanks for watching and goodbye.